Hi, so in this part we're going to see the calculations involved when we are ionizing an atom. So when we are doing the first ionization energy, so let's say we have gaseous X, which is converted to X plus electrons. So we are removing that electron from an inner shell, from an energy level in the atom, and we are taking it away from the atom. So we are ionizing. So what is happening here? The electron is moving from an energy level n to n is equal to infinity, which means that it's going away. And when it's moving from any energy level to n is equal to infinity, so here the first ionization energy corresponds to the limit of convergence. Limit of convergence, which means that it's the minimum energy required to remove an electron from that atom. So from the first ionization energy, we can know the minimum amount of energy required to remove one electron from the atom. So we're going to use that in calculations. So here we can determine wavelength or frequency of convergence from the first ionization energy of an atom. So these two equations, C is equal to V lambda. So C is the speed of light, V is the frequency that is in hertz, and wavelength here, lambda is wavelength, and wavelength is going to be given in meters. E here is energy. E is energy that is going to be in joules. H is the Planck's constant, and V again here is the frequency. So these are the two equations available from the data booklet that we're going to use in our calculations. So we can relate these two equations, and so from this one we can have, so you see that the frequency is common in these two, so we can relate these two equations. So from the first one, wavelength frequency is equal to speed over wavelength, and from the second equation we can replace this here, so that we end up with E is equal to hc over lambda. So this is the merged equation that we'll be using. All right, make sure you note this down, where E is going to be in joules and wavelength is going to be in meters, and H is the Planck's constant from the from the data booklet, and C is the speed of light from the data booklet. Let's see the first question. So sodium has first ionization energy. So you see here, this is given in kilojoules per mole, so we'll have to change it into joules. So calculate the wavelength for the limit of convergence in the line spectrum. So E is equal to hc over lambda. The E is given in kilojoules per mole, so we'll have to change this into joules, and we need to find the wavelength. So if we need to find wavelength, that will be hc over E. So let's find the energy in joules. So what does that mean, kilojoules per mole? Which means that 1 mole of electrons require 502 kilojoules of energy to be removed from that atom, from that element actually. So 1 mole of electrons, so we can convert that to joules. That's one step. We have to get rid of that mole. So 1 mole of electron is how many electrons? So it's from the Avogadro's constant, we know that 1 mole of electron contains 6.02 times 10 to the power of 23 particles of electrons. So this means that this number of electrons requires that amount of joules of energy to be removed. So 1 electron will require how many joules? So you're going to divide it by this. All right, so that's the energy that's the energy that we're going to get in joules. That's the energy required to remove 1 electron from the element. So we're going to use that in our calculations now. So wavelength is equal to hc over E. Replace in the formula and you should have the answer 2.39 times 10 to the power of minus 7 meters. The wavelength is going to be obtained in meters. You can leave it like that or you can convert that to nanometers. To convert this to nanometers, you're going to multiply by 10 to the power of 9. So that should give you 339 nanometers. Sorry. And this is the answer to that question. Let's see the next question now. This one is pretty easy. So you have to determine the energy in joules to 4SF given the wavelength is this. So hc over lambda. Lambda is given in nanometers, so we'll have to convert this to meters. So we are going to multiply by 10 to the power of minus 9 and we are going to fit in the equation. So if you do that right, you should get 3.06 times 10 to the power of minus 19 joules. I just calculated, I got this one. I don't know if you'll be able to get that answer, but I used the calculated values. This is what I get. So 4SF, that's my answer. The last question. So the last question asks you to find the first ionization energy in kilojoules per mole. So in this question, energy was asked in joules, that I got in joules. Now I want it in kilojoules per mole. Given that the wavelength corresponding to this is 91.6 nanometers. So again, I'm going to use the same process as question number 2. So I will end up with energy in joules, but then I need to convert this to kilojoules per mole. So when I fill in the equation and fill in the values in the equation, this is what I get, 2.17 times 10 to the power of minus 18 joules. So remember, the energy that you're going to get is going to be in joules. Now I'm going to convert this to kilojoules per mole. So that number of joules is for 1 particle to be removed, which means that it's for 1 electron being removed. So to remove 1 electron, I need 2.17 times 10 to the power minus 18 joules. I need it for 1 mole. So 1 mole is how many electrons? It's 6.02 times 10 to the power of 23 electrons. That would require, so 1 electron requires this amount of energy. So 6.02 times 10 to the power 23 electron, which is present in 1 mole, that would require 1,308 kilo. You'll get that in kilojoule. Yes, this is in kilojoules. So when you calculate it, actually you get something like this, 838.4. So you get the idea. So when you so this is in joules and you have to divide it by 1000 to get it in kilojoules. So you have the value in kilojoules. This corresponds to 1 mole of electron, which means that the energy is 13,008 kilojoules per mole. And that is the answer. I don't know how this answer got here, but this is what I get when I calculate it. So if you got the other one by one way or the other, just let me know. Okay, so these are the calculations, and when you're doing these kind of calculation, always make sure that you check the data booklet for the values of H and C, and that you convert all the values of wavelength to nanometers, and that you use Avogadro's constant when required. So if you have to use energy, whenever you see the energy kilojoule per mole, you know you need to use Avogadro's constant. Okay, and make sure that you don't forget to convert energy conversions. So joules, kilojoules. Okay, so that's for the calculations. So thank you, and this marks the end of Unit 12.1 HL.